All right, carboxylic acid derivatives. So we learned a little bit about the reactions of our carboxylic acids in terms of how to prepare them and how to reduce them. The carboxylic acid derivatives are where we're going to spend the rest of our time when we're looking at the acid halide, also called the acyl chloride, to be more specific. The acid anhydride, which is this oxygen sandwiched in between two carbonyl groups, the ester, and the amide. Any compound where carbon has 3 bonds to electronegative atoms, chlorines, oxygens, nitrogens, things more electronegative than carbon themselves, is called a carboxylic acid derivative. So even a nitrile is technically a carboxylic acid derivative. It's a carbon with 3 bonds to a nitrogen, which is more electronegative. So therefore, it is a carboxylic acid derivative, which means that it reacts very similarly to the carboxylic acid. We do have some varying reactivity though. Acid halides and acid anhydrides are relatively unstable. They are more reactive than carboxylic acids. Esters and amides are more abundant in nature and more stable. These are less likely to react than the acid halides or the anhydrides. So we do have a wide variety of types of reactivity, and we'll see a nice flow chart diagram that I've created to help us understand this reactivity. A lot of many esters have a very pungent odor. Some of them smell nice, some of them do not. These are the ones that smell nice. Banana oil, isopentyl acetate, is very, very strong, but it smells very similar to, I wouldn't say maybe natural banana, but definitely banana, synthetic banana. Same with methylbutanoate and butyl acetate. Naming, not as important. We're going to talk about reactivity instead. Proteins are just amide bonds, right? If you ever called it a peptide bond, you're probably a biologist. If you call it an amide bond, you are an organic chemist. So the repeating amide linkages here create the structure of proteins, right? Amino acids are amides. The amino acids are carboxylic acids and amines, and when they react, the nitrogen moiety reacts with the carbon of the carboxylic acid moiety, they make an amide, and that amide bond is something that we're actually going to be able to do at the end of this chapter. Many other compounds feature amides, some just natural sedatives like melatonin, which helps you sleep and all sorts of stuff. All right, so moving on to reactivity. When we think about carboxylic acid derivatives, they are electrophilic at the same exact carbon of the carbonyl, same carbon of the carbonyl we've been dealing with before, right? Because of the polarity. Now this is also a polar bond, right? So we're seeing induction and polarity at 2 different positions attached to the carbon electrophile. So reactivity on this list is really determined by induction, resonance, sterics, and just quality of the leaving group. Leaving groups here are highlighted in red. And those leaving groups are the thing that we are going to be really isolating ourselves from. We're going to start with the acyl chlorides, and we'll see all of the reactions that those can do. Then we'll go to the acid anhydrides, and then the esters, and then the amides. So looking at this list, most reactive at the top, biggest reason is for the idea that the chlorine is very electronegative. It is a very good leaving group. I just kind of want to draw the leaving groups that we're talking about. When that chlorine leaves, it leaves a Cl minus. That is a very stable anion for reasons that we know from before, like REO from way back in chapter 3. When the acid anhydride gets attacked and substituted, the leaving group is a carboxylate ion. And we know that is stabilized by resonance. When the ester gets attacked, the leaving group is an oxygen. When the ester gets attacked, the leaving group is an oxygen with a minus charge. Can also be mitigated in just a second, because I know that already might start worrying people. Wait, oxygen is a leaving group with no resonance. What, Lauren? Yeah, I know. This is why we're decreasing reactivity as we go down this list. Nitrogen with a minus charge, super reactive, right? These are less stable. So we will start to see how these, when we get down to their substitution reactions, those are not going to leave as bases. They're more acidic solutions. And because of the quality of the leaving group as a base, we actually have to mitigate that by using a slightly more acidic solution than the first two. Very stable up here. All right, so the more stable the leaving group, the more reactive the original reactant, right? So acyl chlorides are the most reactive derivatives, primarily induction, right? The electronegative chlorine enhances the electrophilic character of the carbonyl. Chlorine atom does not donate much electron density to the carbonyl. It does have the ability to resonate. We've talked about chlorine and other halogens in our aromatic chapter as an actual donator of resonance. They're not great. They don't like to donate electron density through resonance, but they physically can, okay? So the major reason why chlorine is the most reactive here out of the groups is primarily because the leaving group is the best and induction occurs. Amides are the least reactive derivative because induction, the nitrogen atom is less electronegative than carbon or oxygen. So it's the least amount of induction. Resonance with the nitrogen contributes a significant amount of electron density to the carbonyl. So because nitrogen likes to donate electron density and hold a positive charge, this final structure here in the resonance is a significant contributor, which means that the carbon of the carbonyl is less electrophilic. Aldehydes and ketones are also electrophilic, but they do not undergo substitution, right? We saw how these groups can be added to, right? We can add to the carbon-oxygen double bond in aldehydes and ketones. However, now we have leaving groups in our carboxylic acids and their derivatives. So they can actually undergo what we call nucleophilic acyl substitution. Acyl is a common name for the carbonyl group. So we can see how whatever, we'll abbreviate it Z, whatever the leaving group is. That could be the chlorine, it could be the oxygen of the ester, it can be the oxygen of the anhydride, or the nitrogen of the amide. All of those can undergo a substitution reaction instead of just an addition. Overall, the reactions have very similar mechanisms, right? We're going to have a general mechanism that has two core steps. The two core steps will be a nucleophilic attack, which means whatever nucleophile is over the reaction arrow, it will attack the carbon of the carbonyl, kicking up the pi bond. We do not do an SN2 reaction or an SN1 reaction. Those are on sp3 hybridized carbons. Here, our electrophile is sp2 hybridized, right? Trigonal planar. What does form is that carbon of the electrophile after the first step forms a tetrahedral intermediate. And then the lone pairs from the oxygen can drop back down, which will kick out the leaving group. If the reaction occurs, it will kick out the original Z atom, right? The nucleophile will be more stable to stay on, and it will kick out Z. And Z minus, right? The loss of the leaving group has to be stable as well, right? So we need a leaving group that is stable. Excellent. And we'll make that new bond. It was carbon to Z, and now it's carbon to whatever nucleophile we use. H minus and C minus were never kicked out in the previous chapter, which is why now we are going to see that carboxylic acids and their derivatives have a much different mechanistic approach. All right, proton transfers can occur in these reactions, primarily when we talk about the less reactive carboxylic acid derivatives. And so we'll start with basic conditions, but once we start moving into the esters and the amides, we'll start to see that proton transfers might be peppered in. Now, up to 3 proton transfers may be necessary in our mechanism. So whether the conditions are acidic, neutral, or basic, you will have to decide whether the proton transfer happens first or not. So let's talk about reactions of acyl chlorides. There's a lot of them here. The first one is going to be an acyl chloride becoming an acid anhydride. Now, what we'll see is the acyl chloride can go to make any of our other derivatives very easily just by sprinkling in an acyl chloride with an acetate ion or a carboxylate ion. We will get a nucleophilic attack. We form the tetrahedral intermediate. And then when that oxygen rolls its electrons back down and kicks out the chlorine, chlorine is the most stable leaving group. Chlorine is more stable than our nucleophile leaving. I'll draw Cl minus just so that we know it's the leaving group and it's more stable. And that's it, right? It's going to be forming the acid anhydride by reacting an acyl chloride with our carboxylate ion. Second reaction, acyl chloride to a carboxylic acid. What we need for this reaction, which I'm going to use the exact same acyl chloride, is water and pyridine. Pyridine is a base. It's an aromatic compound that's very stable. Nitrogen lone pair right here is not aromatic. That is going to be basic, right? So we'll see that that reaction will be done in a basic solution, okay? So first step, oxygen in water attacks the carbon of the carbonyl, makes the tetrahedral intermediate. And then a proton transfer is necessary. Water is still a great leaving group compared to Cl minus. So we want to prevent HCl from forming, and we want to prevent any water from getting kicked off. And so we will deprotonate that oxygen so that it's not a good leaving group anymore. And then the oxygen will reform a carbonyl, kicking out the Cl minus. So the exchange here is going to involve one proton transfer. And that proton transfer will be between pyridine and the protonated alcohol. You can do this reaction, same exact one, to make an ester. Acyl chlorides can go to make esters. The only difference here with this reaction is instead of water, you will use an alcohol. Any old alcohol that you want with pyridine. Sometimes pyridine is abbreviated PYR. Under the reaction arrow, just be aware that means pyridine it means you're in a basic solution. Mechanism is the exact same. So take a minute to go over it or look at it in the textbook. Okay, same exact mechanism though. The only difference is instead of H2O and deprotonating the H2O, you're deprotonating the protonated alcohol. Last one. Acyl chlorides. 2 in a mid. Now what's great about an amine is that an amine itself is a base. So you can see any sort of amine here as long as it is ammonia, a primary amine, or a secondary amine. You cannot use a tertiary amine because a tertiary amine does not have a proton, and you do need to be able to deprotonate this nitrogen. Let's go ahead and see why. Nitrogen will attack the carbon of the carbonyl, making the tetrahedral intermediate. Hang off those 3 hydrogens. Nitrogen gets a protonated charge, +1. A second equivalent, NH3. Just like the nitrogen of the pyridine was used to deprotonate the nucleophile. Same idea here. Then our tetrahedral intermediate can collapse back down and kick out the good leaving group, Cl-. And we do make NH4+1. Typically, we see that these 2 come together to precipitate out to form a salt, or at least can be isolated in an aqueous solution of a salt. All right, lots of different variations, right? The only ones that we will go over in class are using lithium aluminum hydride. That is going to do a substitution reaction, just as we saw before. And then looking at lithium aluminum derivatives, we'll do this in class where we can stop midway. All right.